These are the video notes for Unit 9, the Volumes 1 notes, which I am referring to as disks along the horizontal. Before I go and start in on example 2, we did example 1 in class, I want to try and show you this little video that I found online. What you've got here is someone has constructed the graph of y equals square root of x. That's this curve here. The graph of y equals 1/10 x. That's this line here. And the graph of x equals 4, which is this line here. And then we'll play this video from here, and they shade this in, and then this is the cool part. They're taking that shape. Let me actually move this back just a second here. So we're taking this shape, and then we're going to rotate this shape around the x-axis. And of all the things I've seen on the web, this is the best sort of visual to show what's going on when we rotate the shape around the x-axis and what we end up getting. Alright, so the shape, the volume that we end up getting when we take that kinda triangular shape and rotate it all around the x-axis looks like this. It's kind of donut-like. I'll actually play this through till the end, because what this is doing is it's going through and showing this technique of finding the area of a washer, and this is the washer that they have here, and this person is just showing us kind of how this washer is constructed. And the technique for integrating then would be to find a little washer down here, washer here, find all of the washers as you go along the x-axis. Right, so let's get back to our notes if we can. Excuse me as I try to find them here. Alright, so here we are. So we'll go where do I want to be? Hold on. I had this set up for us. There it is. Okay, so for example 2, this is example 2. And we've got here in the red, I've already graphed y is equal to the square root of 36 minus x squared. And that's going to give us this semicircle here. And then we're going to take this semicircle and we're going to rotate the semicircle around the x-axis. And if you think a little bit about what's going on here, we'll do it sort of a different color. So when we take this semicircle here and rotate it around, we'll get a disc like that. Here we'll get a disc sort of like that. Here we'll get a disc like that. And you should see that as we get all of these discs, what we end up with is we have described good thing that I can erase. We have described let's spell it correctly. We've described a sphere, right? And the sphere has got a radius of 6. Now, traditional geometry tells us that we want to find the volume of a sphere with radius 6. Let's see, which way am I going to go? We're going to go, we would have, so the volume of a sphere with radius 6 would be 4/3 pi r cubed, which in this case would be 4/3 pi times 6 cubed, which is going to be, when we multiply 6 cubed, multiply that by 4/3, we would get 288 pi. Right. Now if we go and we do this using the integration technique that we worked with in class today, what we'll do is we'll take the area of all of these disks, and let me just kind of draw out one of these disks for us. Right. And the area of this disk here, let's actually kind of shade its face. Right. So we use this as our sort of template disk that we're looking for is the, not the area, the volume of that disk, right, is going to be the radius, and the radius in this case is going to be the distance from the x-axis to the curve, right? And again, this here, that distance right up there, that y, if you will, is the square root of 36 minus x squared. Right? So we would end up with that being our radius. We're going to take that radius and square it and then multiply it by pi. So to find the volume, so the volume is going to end up being equal to excuse me as I get my pen correct, volume is going to be pi times the radius. Well, the radius is 36 minus x squared, and that's going to get squared, right? So this right here is the volume of one of the disks, this disk right here, and we're going to integrate, from over on the left side. We start here at -6, and then we'll work our way all the way across to here, to +6. So low bound of -6, higher bound of 6, and we're going to be finding the volume of each one of those disks as we move along from -6 to 6. Right? So now going to the calculus of it and writing this out. So we're going to end up with the integral starting at -6 out to +6 of the each one of those disks. Well, the area of each one of those disks is going to be pi times the square root of 36 minus x squared, all of that squared. All right. This piece right in here being my r, right? So this is pi r squared, and then we're going to multiply that by the width, and the width is dx, right? And then if we do this out, the constant can come out front. Put that there. And then if we think about that shape of that sphere, well, we're going from -6 to 6, and it's got two parts. It's really the -6 to 0 part is the same as the 0 to 6 part. So what I'm going to do is I'm going to take the integral from 0 to 6, and then I'm going to double that. So I'll put a 2 out here. So I'm going to take 2 of those, and then we're going to take the square root of 36 minus x squared, and we're going to square that. That will give us 36 minus x squared dx. Right? And now we're all set up to do the integration, which will get us, so this is going to be equal to 2 pi times, we'll do the antiderivative of 36, 36 x minus the antiderivative of x squared, which is going to be 1/3 x cubed. And we're doing this from 0 to 6. Which is equal to 2 pi times 36 times 6, 36 times 6 minus 1/3 6 cubed, right? All of that is the upper bound minus the lower bound, which we plug in 0 for both. For x, both terms end up being 0, which then is equal to 2 pi times 216 minus 72, or 288 pi. And lo and behold, we get the exact same answer. Right? 288 pi here, 288 pi there. Right? So that is example 2. I will put example 3 and example 4 in a separate video.